So now we're going to dig in a little bit to what's called the kinetic theory of matter. And the idea is we want to relate the individual motions of particles in a gas. So particles in a gas are just zigzagging around, knocking against each other. And mostly we're going to say they obey Newton's laws, and they're just traveling particles that don't interact with each other except when they collide. And we'll say that they're mostly just colliding with the walls of the container. And we'll say they have zero volume or negligibly small volume. And so this sort of justifies the original form of the ideal gas law. And then we're going to take that motion in Newton's laws and relate it to the quantities we measure for gases like pressure, volume, and temperature. So to start with, we're going to make a few assumptions. So the first one is we're going to start out with a large number of molecules, all identical. What's a large number? Well, as large as it needs to be. Avogadro's number is a mole. It's 10 to the 23rd. We're going to have a whole lot of molecules. The second one is so the first law is we have a large number of molecules. That seems pretty straightforward. We already calculated that in a cubic centimeter of air, there's 10 to the 16th or something like that. The second one is that molecules obey Newton's laws, and they're in constant motion that is isotropic. In other words, there's no preferred direction. They're going in any direction, whatever their last collision had them going. They're small compared to the space between them. If you packed all the molecules into a solid, they would take up a tiny fraction of the volume of the container they were in. And so we're going to, this kind of gets us away from the idea, the corrections we had to do to the ideal gas law. All collisions with the container and with each other are elastic. In other words, they're not losing energy or transferring energy to the walls of their container. It's a solid container that's rigid, and they're just bouncing off the walls of the container. So we're going to make a few other assumptions that I won't list here, but I'll just talk about. First, we're going to let the container be a rectangular box. That's going to make it easier for us to calculate forces and relate those to pressures. But we'll generalize after we do that. We'll consider a monatomic gas like helium or something like that just for our discussion. And we'll assume that they just have the only energy they carry is translational kinetic energy. So they don't rotate or vibrate, and they're not carrying potential energy somehow stored in them. They're just tiny particles that are bouncing around with their motion. So let's do a little a simple diagram. I'm going to draw a box here, but I'm just going to draw one wall of the box. Well, I'll sketch the rest of the box and I'll erase it, right? And so I'm going to say, you know, I've got some kind of box here, and it looks like this, right? Like this, and like this. It's a 3D box, right? And the particles are inside it, bouncing around. Right, and they're going in all different directions, and they just have collisions with the walls. Right, and so I'm going to look at what happens on this wall over here. So I'm going to pick this wall here, and I'm just going to look at what's happening on this wall. Right, and so we're going to look at what happens with one particle, and we're just going to take an average case. And so here's a particle here, and it collides with this wall, and then it bounces off this way. And so this is V, and this is V prime. And notice the magnitude of V is equal to the magnitude of V prime, because the collisions are elastic. The collisions are elastic, and so no energy is transferred. And so the speed they come in. So basically what happens with this guy is, if I look at the components of his velocity, he's got initial Vx this way. That's his initial velocity. And he's got initial velocity this way, Vy. And then after the collision, his Vx is reversed. So he's got the same Vy. It's just the components. I'll put a prime on this guy. And then he's got a Vx prime here. And just like here, the magnitude of Vx is equal to the magnitude of Vx prime. In other words, he just reflects his x velocity back in, and his y velocity does not change, and so he goes in this way and he comes out that way. And so we want to kind of look at what happens to these collisions in the wall. Clearly, these are finite particles, and they're bouncing off the wall all the time, and there's a large number of them, so they're like BBs going pap, 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 pap off the wall. Well, if there are enough of them, then those collisions are just sort of continuous. And so we're going to look at what is the force on one particle during the collision. I'm really not going to calculate this, but I'm going to talk about it, and then we're going to just kind of do an average and figure out, well, okay, if one particle gets this much force, what's the force on the others? So if you remember from Newton's second law, force is equal to mass times acceleration, and we kind of rewrote that as force is equal to mass times the change in velocity over the change in time. Or this is, we could say the mass times the change in momentum. Sorry, we can call this the change in momentum over change in time if we wanted to. But we're going to kind of look at this piece here, and we're going to say, look, so this is our wall. We're going to draw a little coordinate system up here. We'll call this, we might need 3D, so we'll call this the z-axis. The y-axis will go into the board, and the x-axis is going this way. And so it's a right-handed coordinate system. So that's the x, that's the y, and that's the z. And I'm kind of doing it like that. Okay. And so for our one little particle, we can say, look, the x direction force due to this wall is only going to exert x direction forces. It's not going to exert forces in the y direction, because it's the wall's facing the wall's in the yz plane, and so all it does is a particle goes in and its x direction velocity gets changed. And so that's the mass times the change in velocity over the change in time. Well, we know what the change in velocity is. It's the mass times Vx prime minus Vx, which is just, since this guy was going this way, he was negative, and so that's mass times Vx. If I just want the magnitude, Vx and Vx prime are the same, minus mass times minus Vx. You get it? Because when it's going in, its velocity is negative. When it's coming out, it's positive over delta t. And so that's just 2m Vx over delta t. Well, strictly speaking, we would say, well, the delta t is the time for the collision, right? And it's just while it's in contact with the wall. But we want to look at the spirit of this is we're going to look at what's happening as the particles are colliding with the wall. And so we're going to say, well, how much time does it take all the particles to hit the wall? So assume all have the same Vx. So this is just like the average x velocity. Normally they're like popcorn, they're all going at different speeds. But we're going to say they all have the same x component of velocity. Half of them are going this way and half of them are going that way, right? And so in time, delta t equals L divided by Vx right? They all have the same x velocity, right? And so if I wait a certain amount of time, if I take the time it takes the particle that's all the way at the other end of the wall moving at Vx, then Vx times delta t is L, right? That's how I'm picking my delta t, so that it has enough time to travel all the way across and hit this wall. And so this is the amount of time it takes all the particles moving on the left to go all the way across and hit the wall on the right. And that's what I want to do. I want to say, look, each one experiences this much force, and that means they exert that much force on the wall by Newton's third law. And then in this time, delta t is L over that average velocity. Half of the particles in the box, all of them initially moving that way, will have hit this wall and exerted that much force on the wall. And so on the next sheet, we're going to sort of use that to figure out what the average force on this wall is. So again, here's my box. I'll just look at it from a 2D view now. It's full of particles. They each have an average velocity Vx going this way. And so the time it takes for one at the far end, this length is L. I don't know if I said that on the last page. So this is L. Their velocity is Vx. And so delta t, the time it takes for the farthest particle to hit this wall one time, is velocity is distance over time, and so time is distance over velocity. This is the time for and that means all the particles that were moving this way that had an x component in this direction, which is half the particles in the box, all the particles that had an x component in this direction will, in this time delta t, have bounced off this wall, because the farthest one does it, and so that means all the ones that are closer do it. And we just said the average, the force for one particle is 2 times the mass of the particle times Vx squared over L, right? And so that's the average force on the left wall, or really on any wall, due to the collisions with the particles. And so this gives us a formula to work with for these forces. Now we know that so this is kind of, we're talking about kind of an average force here, and so I'm going to write it that way. And so I'm going to say, look, v squared is equal to vx squared plus Vy squared plus Vz squared, because this is going on in all dimensions, right? And so if I say they all have the same average velocity, then I say v squared is equal to 3 times Vx squared, say, if these are averages. Average. Hopefully you see that, right? It doesn't just have an x component. On average, it's got an x component, a y component, and a z component, and so those all add up. And so then I can say, look, the average force is equal to n times m v squared average over 3L. This is the average force on a wall based not on the average x velocity, but just on the average velocity. Right. And so this is just a little more general way of writing. I haven't really said anything except that I've said, look, I'm going to use this v instead of that component v, but I'm still looking at sort of averages, right? And now I can calculate the pressure. The pressure is equal to the force divided by the area. That's from all the way back in our definition of pressure. Right? And so if this wall has area A, then this is equal to 1 over A times n m v squared average over 3L, which is n m v squared average over 3 times the area times the length. But the area times the length, if it's a rectangular box, which we said it was at the beginning, is just the volume. And so it's n m v squared average over 3 v, right? And so now this is what I have. I have P is equal to n m v squared average over 3v, or PV equals n m v squared average over 3. This starts to look a lot like the ideal gas law, doesn't it? If I come over here and I erase a little bit, right, I can say we know that PV equals NKT, and so that means KT is equal to MV squared average over 3. And so I can write this as MV squared average equals 3 KT. And if I multiply each by a half, I get 1/2 MV squared average equals 3/2 KT. In other words, the kinetic energy, the average kinetic energy of the particle in the box is 3/2 KT. And really, if you go all the way back to here, it's 1/2 KT for every one of the 3 dimensions. And so this is why we say the temperature of a system is directly related to the kinetic energy of the particles in it. What you're really measuring when you measure kinetic energy, temperature, is the average kinetic energy of the particles in the box. Notice that when we arrive at this, we didn't put anything in particular about helium in here. We didn't put any molecular mass. We said helium, it could have been xenon, it could have been a lot of different things, right? What this says is the kinetic energy of whatever particle is in the gas is 3/2 KT. In other words, if the temperature is what it is, then the helium molecule has the same kinetic energy as a xenon molecule. So a superlight molecule at the same temperature will have the same kinetic energy as a much heavier molecule. So the lighter molecule will have to move faster to have a smaller mass and the same kinetic energy, having a smaller mass to have the same kinetic energy.